Welcome to a review of basic chemistry and primarily an introduction to the periodic table of the elements, brought to you by the academic alchemist. So what is chemistry? Well, chemistry is many things, but basically it's going to be a study of how the world works, how the universe works, although mostly the day-to-day world that we live in, not necessarily the tiny micro subatomic world of quantum theory. It doesn't really explain everything in the big scale in space. Here's a picture of the pillars of creation in the Eagle Nebula. And yet we can study a lot about space using chemistry, figure out what elements are inside of stars, a little bit about how stars are formed and how they die. So we're going to get down to some basic questions to start, like, for example, what's a chemical reaction, what's a physical reaction? Here we have some water. I'll move that over here. Here we have some steam. And then here we have some ice. What's the difference between these things? We all know that these are made out of water, H2O, hydrogen, and oxygen, but some are cold and hard, and some are gaseous. What's the difference between all these things? Well, those are examples of the same compound in different forms. We call those phases. So those are changes that can happen to an element, or a compound, or a molecule, and they can happen by changing their phase, their state of matter, and those are physical changes, not chemical changes. Now, if we were to take this piece of paper, though, and light it on fire, would that be a chemical change or a physical change? Well, the basic test is, does this change the chemistry of that substance, of the cellulose in the paper? And I would argue that clearly, when we're done with that fire, we end up with some smoke. Ooh. And we end up with some charred remains. We have a little bit of fire in there as well. And this is a one-way reaction. We can't go backwards and reassemble these ingredients and make paper. So this would be a chemical reaction. We have the cellulose, all those hydrocarbon bonds. The hydrogen bonds are broken, releasing a bunch of energy. The carbon remains as soot. A lot of particulate matter, some of the trace elements and a lot of the water vapor get turned into smoke, and those things have been separated chemically into different molecules and can no longer be put back together. So that would be an example of a chemical change. Unlike our ice, water, steam example. Now, here's the main character of our little drama here. Back in the 19th century, Dmitri Mendeleev was the leading chemist in the world, and he did a great job of analyzing what was known about the 50-some elements that people had isolated, and he focused on their atomic masses. And he predicted that there would be more elements discovered, and he put them in a particular order that he described as his periodic table, which allowed him to make these predictions. So these predictions of Dmitri Ivanovich Mendeleev were made possible by his rather impressive table of the elements. He basically organized these guys into a system that allowed certain patterns to be revealed. So he said, maybe I'll put them in order of their atomic masses, which he decided was the most important part of this, but allowed him to realize that actually the most abundant element in the entire universe, hydrogen, had only one proton, and the second most abundant element in the universe, helium, has 2 protons. And so he actually then created the atomic number to reflect the number of protons. So lithium has 3 protons, the atomic number 4, beryllium has 4 protons, 5, 6, 7, 8, 9, 10. So you'll notice a sequential set of numbers that will immediately tell you the number of subatomic particles in, or at least one of those particles in an element. You could say that, for example, Radon here has 86 protons just by looking at the periodic table, and this is basically the world's biggest cheat sheet. It has a whole bunch of information condensed very nicely into this one table. So we know that, for example, the first row, hydrogen, helium, those elements both have only one valence shell, one outer shell of electrons, and that determines almost all of the chemistry, all chemical reactions and interactions that those elements will experience. Just about everything except for nuclear chemistry, nuclear physics, can be explained by the electrons in the outside shells of an element. So here we have lithium, beryllium, all the way to neon, the second row of the periodic table of the elements. These guys have 2 valence shells. In the third row, these guys have 3 valence shells. So there's certain patterns. For example, if you go down this group, this vertical column here, those guys happen to all blow up if they touch water. If you have pure lithium or pure sodium or pure potassium, these things will absolutely explode on contact with water. Whereas over here in this group, this column is the periodic table is the noble gases, and none of them will react with anything no matter what you do to them. So helium is a pretty safe thing to put into a birthday balloon, even though there'll be candles on that cake. You can't get this gas to blow up no matter what you do to it. And all of these basic understandings you'd learn about in high school chemistry really come from, or their origins start with Mendeleev and his organization of this table and the creation of maybe the most impressive cheat sheet ever created. So, we'll have a series of these screencast lectures about chemistry, and the final one will come back to what are all the patterns we can find in the periodic table. Thank you for joining us. This screencast has been brought to you by the Academic Alchemist.